Hi MOS 4472 team. In this video, we're going to talk about designing systems and databases. In this lecture, I will take you through the following topics. We're going to outline the system development life cycles, or the SDLC stages. We're going to compare two different system development methodologies, and those are the waterfall and the agile system methodologies. We're going to distinguish among some different modern databases. We're going to talk about designing relational database tables using an entity relationship diagram, or an ERD. And we're going to talk about constructing some queries to retrieve data and to answer business questions. Organizations have two options for capturing and processing data. They can either buy an out-of-the-box system or build a system internally. And that choice is really contingent of who the company is, how large they are, what kind of processes they have, and what kind of informational needs, and also what is the budget. The main risks of developing a system in-house include that a lack of management support can lead to constraints in time, financial, and other necessary resources. So it's really important to get top management buy-in so that they act as champions rather than opponents or even neutral parties towards the system. Also, another risk is incompatibilities between the IT structure and evolving technologies. Technology is expanding very rapidly, so it's very important to find synergies between what the organization has and what they need or will be developed to ensure that you can have a more holistic system, because building patches can have disastrous consequences in terms of data integrity. So it's really important to make sure that everything runs smoothly and that synergies are established. Another risk is resistance from key stakeholders may lead to deployment and adoption issues. And key stakeholders are not only senior management, but also the users of the system. The users need to see the benefits of the system, and they need to see a way that the system will make their lives better. A lot of people are resistant of change because they're scared of change. So it is important to be open and honest with all stakeholders. And the other issue is inadequate training can lead to poor adoption. A lot of organizations spend a lot of resources on developing the system, but they forget that training also requires the sufficient amount of time and also the correct training processes and procedures, which could be costly. So maybe you need to develop manuals, instructional videos, have a trainer come in to show employees how to use the system. So training is very, very important. When an organization decides to develop a system, oftentimes they go through the system development lifecycle. And this is just a project management framework with clearly defined stages for creating and deploying new systems. And it could be subdivided into three categories. You have pre-implementation, the building, and going live and beyond. Part of pre-implementation includes planning, analysis, and design. With building, you have development and testing, and going live and beyond, you have implementation, but also maintenance. And we will go into further detail of what these stages are in the upcoming slides. This is a great visual from your textbook that breaks down the 7 stages of system development, and it discusses what occurs at each stage and the key outcomes of the stage. So when we look at pre-implementation planning, The main goal is to identify the necessary resources needed for the project. And the key outcomes, you should have roles and responsibilities of the project team. You should conduct a feasibility study and create a project plan. Similarly, analysis involves identifying user requirements. And once the stage is complete, all the requirements are documented. Then you have the design stage, in which programmers translate requirements into specifications. This includes creating a conceptual design, figuring out what the technical specifications are, and creating a system model. Once the system is designed, it needs to be developed, and this is where the system's actually created. And the key outcome is system documentation that shows kind of a blueprint of what the system is and how it functions. Before anything can be provided to end users, most organizations do testing to validate the code and the system, ensuring that there are no bugs or glitches. And the key outcomes are test cases, test reports, and detective reports. Then we have the go live and beyond stage, where the system is actually implemented to the end users. And the key outcomes of that are user manuals. You have your policies and procedures, a features list, an implementation request, and various approvals from management. And then once the system is working, you constantly have to maintain it to make sure it's operating properly. And part of the maintenance outcomes are updating policies and procedures, updating user manuals, and creating maintenance logs of all the work that is being done. Developing a system involves many people, and these people can be divided by their roles and responsibilities. So let's take a look at that. We have the IT steering committee, who are representatives from the business area throughout the company, including the IT department. And their most important responsibilities are to approve and prioritize proposed projects for system development. There might be multiple departments requiring multiple systems, so they need to prioritize what should be created first, given the resources that the organization has. Another role are end users, and these are the individual employees that are going to be using the system in their day-to-day job functions. These are the people who need the system to work a certain way. And their responsibility is to identify their business needs, propose system to address those needs, and find final product in daily job routines. Then we have our lead system analyst, who manages the development team that programs the project, and they work with end users to directly develop a plan for the system, including what the specifications and logic is going to be. Then we have our core application programmers, who are members of this development team, and they report directly to our lead system analyst, and they're responsible for developing the code that becomes the system. So let's look at the pre-implementation stage in more detail. During the planning stage of the project, an organization needs to define what the scope of the project is, identify the necessary resources needed for that project, determine the likelihood of success, which is done using a feasibility study, and you always need a project plan, which identifies the scope of the systems and also the goals of the project. And your project plan comprises of the following 3 elements. We have critical factors required to make the project successful. We have a definition of the project scope, including an overview of the goals of the projects and the limitation. And then we have milestones and responsibilities that break down the project goals into timelines and identify the individuals responsible for each goal. So this is a more defined plan where you include both responsibilities and the people assigned to perform those responsibilities. As we talked about, part of planning is including the creation of a feasibility study. And what a feasibility study is it's an analysis of the technical, economic, and operational factors that will impact the project. And it is during this stage that the build or buy decision is made. And the key part of the feasibility study is to decide whether the project is realistic at a given point in time. And the key questions to ask during a feasibility study, you have to look at the technical perspective. So the questions you're asking, do we have the talent necessary to build the program? Or do we need to hire a contractor to perform it for us? And then, should we buy a system instead of building it? So you're questioning that make or buy decision right there. Then you're looking at the economic feasibility. So do we need the system? Do the benefits of the system outweigh the cost of development? Should we support the system locally or choose a cloud-based delivery method? And then we have the operational feasibility component that looks at how well will the system integrate into the company's current system and environments. We looked at the planning phase. Now we're going to move on to the analysis phase. So during this stage, system analysts meet with end users to understand business requirements of the projects. And you need a requirements definition. And this is created through formal documentation, and it identifies the final project goals, steps needed to achieve them, and outlines the overall system plan. So now we have created the plan, we analyze the project. The next stage is to design. And during the design stage, you define the requirements into technical specifications. And here are the following functions that need to be performed. The lead system analyst needs to create technical architecture specifications that identify software, hardware, and network technologies that the system will need. Then the lead system analyst creates flowcharts and data flow diagrams to create a systems model that describes in technical detail how the system will interact with users and other technologies and system process and components. Lastly, the lead system analysts and core programmers will create a mock-up of the graphical user interface, or the GUI, that shows the screens that will allow the users to interact with the system. So you need to make the GUI to see if your end users are satisfied and it looks friendly and workable from their point of view. You don't want to build something that your end users are unhappy with. Now we move into the system build phase, and the first step is development. And during this stage, programmers create the system based on technical specification identified in the design phase. Programmers will need to write code that is based on the requirements and design specifications, and one that is compatible with other systems throughout the company and also error-free. One of the reasons we're going to talk about testing next, because it is critical for the system not to have any bugs or errors. Now that the system is built, it needs to be tested by an independent team. As you probably know from your own reviewing of your own work, it is much easier to have a third party review your work. They're more likely to find errors and problems. We as humans often see what we want to see, versus what's on that page. So it always helps to have a fresh set of eyes. And this independent team evaluates the system against the design specifications and requirements definitions to ensure that what was built is exactly what was wanted. And questions system testers need to answer are, does each piece of the system work correctly? Does the system work together as a whole? Does the system work with existing systems that it must connect to? Does the system accomplish its primary purpose? And this is answered by a select group of end users during user acceptance testing. And user acceptance testing basically has a group of end users try the program to see if it works the way they want it to. Now that the system has been tested, the next stage is to implement it. And when a system goes live, it becomes available to users. However, companies have some choice in which kind of implementation method they utilize. There's advantages and disadvantages of each method. Each company has a unique choice to make based on their thoughts, requirements, budgets, timelines, etc. So one strategy is a direct cutover, and think of this as turning on a light switch or a computer. It's either powered on or off. There's no overlap between the old system and the new system. The new system starts running and the old system is gone. Another methodology is to utilize parallel implementation. Utilizing this methodology means that the old system and new system run concurrently until there is confidence that the new system works properly. Obviously, this is a lot more work because you have employees inputting information into two systems for a period of time. Another implementation option is utilizing phased implementation. And in this case, systems are divided into modules, and one module is implemented at a time. So for example, we might start with implementing the finance module. The finance module goes live, the finance people use that module. Some time passes and we find that it works, then the production module might go online, or the supply chains. And the key is that it's phased and only one module is introduced at a time, and all of the people who aren't within that module are utilizing the old system until their time to go live comes about. Then we have a pilot implementation. This is usually done in large organization. And basically what occurs is that individuals are divided into groups, and some users try the new system, everyone else is using the old system, and then when the pilot group doesn't have any problems, everyone switches over. So for example, if I have an international company headquartered, let's say in like 20-30 countries, we might use Canada as our pilot country. If the new system works well in Canada, then we can introduce it to the rest of the world. The last stage of system development is the maintenance stage. When maintenance begins, you usually have multiple groups using the system. And during this stage, the system is monitored, updated, and changed based on changing business needs. And changes to the system have to go through the company's formal change management process, which is part of the greater information technology environment. There are two popular methodologies of implementing the SDLC framework. One is the waterfall system and the other is the agile system. With the waterfall methodology, it's very sequential and it breaks down the SDLC into formal stages, which must be executed in a linear fashion. And each stage flows downstream to the next stage sequentially. So one stage has to be completely finished before the other stage begins. There is no overlap, and every stage is performed in its entirety. And it usually uses the 7-stage SDLC framework, but companies might customize the approach and use 6 stages or 5 stages. That's really up to the organization. There are some risks related to the waterfall methodology. One is that if users change their expectations, those changes can't be easily integrated into the system, because remember, you're going in a linear fashion. Changes in business processes that use the system, once again, create issues within the system. If there is turnover in the leadership, this might cause the changes in requirements to make the project obsolete. And sometimes there can be a disconnect between developers and users that might prevent the project and system to be implemented, because end users don't see the system almost until the very end, once it has been fully developed. The alternative methodology that can be used in system development is the Agile methodology, and it is also a group of SDLC methodologies, and this type of methodology focuses on iterative development, collaboration, and self-organized cross-functional teams, and it is characterized by multiple short cycles of work that simultaneously include multiple SDLC stages. So you're doing the stages concurrently, and it involves end users in real-time decision-making as the project progresses. Agile breaks the project into smaller pieces, involves end users. By the end of the project, then end users know exactly what the system is that they're receiving, because they have been part of the design, feedback, and testing phase. The main focuses that individuals utilizing the Agile look at are ensuring customer satisfaction, supporting trust and motivating people, encouraging collaboration between business stakeholders and programmers, regularly reflecting on ways to improve the project, adjusting to changes in mid-development, which we've noted was a weakness of the waterfall system, and creating self-organizing teams of equals without a structural kind of hierarchical leadership. So the Agile system utilizes something called a Scrum, and this is a set of project management practices that focus on daily communication and flexible planning. The flexible planning allows for changes mid-project, and these changes should not impact the budget or the timeline. Usually the project timeline is very set with Agile. And the Scrum breaks the system down into short cycles. And after each cycle, the team reflects on the successes and failures, and appropriate adjustments are made to continue on to the next cycle. So it's very flexible and plans will change. And this type of methodology involves 4 parties. We have the end user and the 3 roles of the Scrum team. Oh, sorry, we need to stop this video. Say hi, class. Say hi, class. So let's talk about the 4 roles involved in the Scrum project, and let's see what their counterparts would be in a SDLC system. So we have business stakeholders, which are synonymous with end users. And these are individuals who will use the system in their daily functions. And they need to communicate regularly with the product owner and provide real-time feedback about each project iteration. We have a product owner who is synonymous to the lead system analyst, and they're really the champion of the system and understand end user requirements, communicate the requirements, and feedback back to the core development team. Then we have the Scrum Master, and the Scrum Master is a role that is unique to this type of project, and they're really the champion of the core development team, and oftentimes they're referred to as the servant leader, and they motivate the core team, ensure core development team focuses on agile principles. They try to clear obstacles that come into the core team's path, and they facilitate the dialogue of the team. So they're kind of like the cheerleader, mentor. They set the tone. And then we have our core development team, and this is a set of self-organized programmers without any formal leadership. They have their Scrum Master, but they don't have a leader. And they basically conduct the project execution and testing. They manage timelines, their responsibilities. They have to be open to the Scrum Master's motivation and guidance. They have to commit to transparency and accountability within the team. So everyone works together as a self-managed team. To execute a project, Scrum time boxing is used, and this is done to efficiently integrate feedback and respond to changes in real time. And it is essential to have great time management with these projects. During the project, the team conducts sprints, and these are just the single iterations of the system project, and they include multiple SDLC stages. So you might be planning, analyzing, developing, and testing all at once. And these sprints can be either monthly or weekly increments. However, for our system projects, the most common is 2 weeks. And time boxing allows a length of time to each activity to both define the activity and limit the amount of time dedicated to it. And it's used to prevent scope creep and extend deadlines. So you have a very set time that each activity should take. And to define scope creep, this occurs when a project evolves during development beyond the original specification, and it just becomes too large to be designed and implemented during the project timelines. And everything is subject to change during the agile system development except for time boxing. The final deadline can never be extended. The scope of the project will change, and there might be less things built than expected, or different things might be built, but they always have to be completed within a certain amount of time. The tools used to keep the team accountable are called Scrum artifacts, and these ensure transparency and clear communication of project information to all parties. And the 3 main artifacts used are the product backlog, and this is just a list of the desired product features in the system being developed, and each feature will have its own item of the backlog, and features are built in order of priority and are categorized as crucial, fundamental, or nice to have. If time runs out after the fundamental features are built, all remaining features can be created as future update, and the project ends then. Then we have a sprint backlog, which contains what the core team will develop during the current sprint, and its features on the product backlog are allocated to the sprint backlog. So it's basically a schedule of when each feature should be done on which sprint. And then we also have the product increment, and that's the current version of the system being developed at the time of the sprint. And this is presented to business stakeholders for feedback, and then feedback is brought back and it adjusts the product backlog. So as you see, it's kind of like a cyclical iterative cycle. So here is a visualization that illustrates the differences between the waterfall and the agile SDLC methodology. The waterfall is very sequential, one step at a time. You can't go back, you keep going forward. Whereas with our agile system development, you do these sprints and you can continuously make changes. So the project is much more open to change than the waterfall. Here is a nice table comparing and contrasting the two methodologies. We have criteria and then we have the comparison between the two. So let's go through it. In terms of requirements and regulations, with the waterfall methodology, there are many initial requirements with little rooms to make changes during development. Whereas with the agile system, we have few initial requirements and regulations, allowing developers to use creativity and improvements along the way. So the project can change and evolve. In terms of leadership involvement, you have project management with a low level of involvement who only wants periodic updates. Whereas with the agile, you have this hands-on product owner who wants to be heavily involved in real-time decision-making and constantly receives feedback. New system versus update. With the waterfall, updating an existing project with clear definitions of change management needs. Whereas with agile, you can create a new system from scratch. From a budget perspective, the waterfall has a firm budget that requires a predictable outcome, hence you're doing this feasibility study. Whereas with the agile system, the budget is flexible and allows expenses needed to prioritize features and increase the speed of completion. When it comes to IT infrastructure, with the waterfall, you have formal procedures already operating under traditional SDLC stages with a corporate culture that supports these traditional methodologies. Whereas with the agile, you have less formal procedures, enabling team flexibility and a corporate culture that accepts failure and trying new things. So you have to look at what type of an organization you're working for in order to see which type of methodology would best fall in place with their existing culture. And then when it comes to team composition, with a waterfall, you have minimum communication requirements and people can be decentralized or in remote environments. Whereas with the agile, you need daily communication between the team and it's important to meet in person and sit in the same office. Now we're going to move on to the next part of this chapter, and that is looking at databases. Databases are used to store and access information. So the consideration that businesses should address when deciding which database to integrate is to consider items such as data variety, looking at whether the organization is going to be collecting structured versus unstructured data versus a bit of both. Looking at the volume of data that is going to be captured daily. So what is the amount of data? Are these needs going to change or stay the same long term? Then we have scalability. What are the current performance requirements and how can they be improved over time as demands increase? And then we have to decide what is the purpose of this database. Is it going to be a data warehouse versus a data lake or some kind of other data system? Probably the most common database used by accountants are relational databases, and these databases store structured data into two-dimensional tables of rows and columns, and data is collected across multiple tables that are connected to one another. And the information that's contained within a relational database from smallest to largest, you start with a field, which is a group of bytes or characters that identify the characteristic of an entity, and the field is an attribute. Then we have records, which are a group of related fields that describe an individual instance of an entity. For example, a transaction is a record. Then we have a file, which is a group of records for one specific entity. And a file in our relational language is a table. Then we have our database, which is a set of logically related files. So we're starting at the field level and growing to a database. Some new terms that we have to learn when we talk about databases are columns, which is a collection of data fields aligned vertically in a table that are all in the same data type, such as text, dates, or numbers. So in our example here, we have an address column, a birthday column, a name column, and a first name column. We know that the first names would be text, birth dates would be a combination of text and numerical, address, same thing, combination of text and numerical. And then we have the field names, which are descriptive labels or names given to a column that identify the contents of the column. And these are also known as headers. So in this example, we have our first name, last name, birthday, address, city, and state. In contrast to relational databases, you can also have databases that are called object-oriented databases, and these are a hybrid that have a relational database framework, but the data is presented and stored in a form other than tables. And this is a benefit because it means that these databases can store both structured and unstructured data. In object-oriented databases, designers determine the data needs and how they'll be connected and what the similarities of the various objects within the data are. And instead of using tables and relationships, a class connects similar objects together. Objects are an item contained within a class, and they're similar to a record in a relational database. And then we also have variables, which are names assigned to similar characteristics of objects in a class. And this is similar to fields in a relational database. And when a user queries a class, all objects contained within the class are returned, and users won't directly query records. So here we have an example. Here we have a class. In this case, it's customers. And then each customer is an object within a class. And let's say we pull on customer 1, we have this customer object, and this customer object contains all these variables. So all this information is collected about this customer. So a very popular database that is being utilized more and more is a NoSQL database. And SQL is just structured query language. So this is the language used to retrieve data from relational databases. But the new databases don't use SQL, so they're called NoSQL. And these databases store each item individually rather than in columns and rows, and they retrieve them by using key values. There is no structure schema, resulting in flexible storage of unstructured data. These databases support both structured and unstructured data and are often referred to as not only SQL, and programming language such as Java, C++, and Python can be used to access this data. Although NoSQL databases can store structured data, they are not ideal for structured data because they are not designed to support transaction processing. NoSQL databases are ideal for companies that want to store and retrieve vast volumes of data, companies that have a lot of unstructured data, companies that have data that changes continuously, and have growth in the volume of data that cannot be scaled appropriately. And NoSQL databases are not very suitable for cloud computing. So you would need to have your own servers and hardware and software for these kinds of databases. We're going to dive more deeply into relational databases because these are the types of databases that you will likely work with as accountants. Tables in a relational database are connected in a specific order, and as more tables are added, more data becomes available. Designing relational databases requires understanding and planning for the data that will be stored. So you have to have an understanding of what you are collecting and how it will be used. And data modeling allows us to document data that will be stored in a database and identify its specifications. And these specifications will include the fields that will be stored, the associations or relationships between the fields and tables, and the rules that will govern these associations. In order to design a database, you need to model how it will be created. And one way you can do this is through conceptual entity relationship diagrams, or ERDs. And these diagrams identify the entities and tables that the database will capture. They model relationships among the tables, and the type of ERD used is usually determined by the intended purpose. We have the conceptual ERDs and logical ERDs, and they're used by business analysts to model the plans for the database, whereas physical ERDs are more elaborate blueprints that are used by database designers who will implement the structure by creating the actual database. So accountants like us can look at conceptual ERDs, but database designers need more information, so they need physical ERDs. A conceptual ERD is the simplest form of an ERD, and it just is created based on business events that are used to define relationships. Here's an example of a simple ERD. We have a customer who places an order. The order is placed for a product. An order is placed at a store, and the store sells the product. So as you can see, we have the connection between the customer and the order because the customer places the order. Where do they place the order? At the store. So we need to link the store to the order. And then they purchase a product. So we need to link the product to the order, but also the product to the store. A logical ERD has more details than the previous ERD because it adds field names to each table, and all field names describe the records that will be collected. At this stage, the field names are conversational terms, but as the database design progresses, they will be replaced by the system field names, or how the system will identify those fields. And you need to create a data dictionary, and a data dictionary provides a detailed description of the data text for the fields located in a table, and it provides descriptions that end users can reference when they need data from the database. So this is kind of like your little dictionary. So for example, if you know that you're looking for email addresses, you look at email addresses and it tells you, oh, these are customer email addresses. As I mentioned, the ERDs are getting more and more detailed. So the final ERD level is the physical ERD, and that physical ERD is the design blueprint of the relational database. It enhances the logical model by adding field names, sizes, and constraints, which are the rules about what can and can't be put in a field. And the physical ERD adds the relationships and the terms to define the items that are used in the database design. When designing a database, it is important to focus on data integrity. And one way to increase data integrity is to reduce data redundancy. And data redundancy is said to exist when the same piece of data is stored in multiple places or multiple tables within a database. And the first step in building a relationship is to ensure that every table has a unique field that uniquely identifies every record within that table. So you have to have a column with a unique field that has a unique ID or something along those lines. And to address this, ID columns are often used, and unique IDs allow a database to retrieve only the record related to that particular ID. And when we think about data integrity from a database perspective, we think about managing data accuracy and consistency, including the management of data redundancy risks. And data integrity is an essential part of ensuring that management receives quality information for decision making. Because remember that we are going to create reports and queries on the data within the database and transform it into information through reporting and analysis. Databases are linked together through the use of primary and foreign keys, and relational databases use unique IDs and relationships to eliminate data redundancy by referencing data a table needs that is already stored in a different table. The unique IDs identify records in the database, and they are called keys, and they are the center of the database relationships. So the primary ID is the unique ID of that table. So each record in that table has a unique ID, such as a customer ID in the customer table. And the foreign key is that ID referenced by another table. So for example, customer ID might be referenced in an order table, but because customers may place multiple orders, this ID will not be unique in the orders table. Then we have our relationship, which is just the connection between the primary key in one table and the foreign key in another. And referential integrity means that a foreign key can't be entered into a table unless it exists as a primary key in a base table. So you always need each column to be a primary key of a table before it's a foreign key. And entity integrity refers to the fact that a primary key can't be null or empty because it's a unique identifier. It should always be filled out. Now let's talk about cardinality. So once it has been established that the two tables are related to one another, the relationship must be characterized by identifying its cardinality. And what cardinality is the numeric relationship between data in one table and the data in another table. So to understand cardinality, you must understand perspective. In a relationship between two tables, there are two perspectives. The way that the first table relates to the second table and the way the second table relates to the first. So think about any type of relationship. For example, a mother-son relationship. To me, my child is my son, and to my son, I'm his mother. So it's the same relationship, but based on perspectives, you identify who you're looking at. It is important to understand perspectives because every relationship is subject to constraints. The constraints are applied to every perspective in the relationship, and there are two constraints. You have a plurality constraint, and this identifies whether the table's records are associated with one or more than one record in the second table. An optionality constraint, which identifies whether the first table's records must have a relationship with one or more of the records in the second table, or if they can be related to none of the records in the second table. This identifies whether the relationship is mandatory or optional. So for example, every order must have a customer, but not every customer must place an order during a certain time period. Now that we know about the rules, we can talk about how we draw them out. So business rules are written statements that precisely capture the business event occurring during a process as it relates to the entities in the database. And when it's written correctly, business rules define the entities, relationships, cardinalities, and constraints of the database. And crow's foot notation is the formal diagramming notation that adds shapes to the end of each line between entities to identify the optionality and plurality constraints. So this table shows the crow's foot notation. Please remember that each relationship will have both a plurality constraint and an optionality constraint. So with plurality, you can have a relationship that one and only one item is linked to the other, or there could be many. So for example, one customer will place an order. There's only one customer per order, but there can be many orders per customer. And similarly, it is mandatory for an order to have a customer, but it is optional for customers to place orders. Maybe someone hasn't ordered anything this year yet. So here are our cardinality notations. We have one and only one, no more than one, at least one, and any. Here are some rules to keep in mind when designing relational databases. Every column needs to contain a single data type, whether it's a letter, number, or date. The primary key can never be empty or null, and this rule is referred to as entity integrity, and it's the one of the most important rules when you're designing a database, because you cannot have an empty primary key because there's no reference back to that table. The foreign key cannot be used in a table unless it corresponds to an existing primary key in the base table, and this rule is called referential integrity, and it ensures that logical dependencies exist between primary and foreign keys. Then another rule is that all fields in a record describe the object identified by the primary key, and relationships are always defined by their cardinality and optionality. So let's now talk about how we as users of data interact with a database. A key characteristic of relational databases is that they can be used to create ad hoc reports for data they store by using a querying language. When I was working at Canadian Tire as a business analyst, we use querying language on Access all the time because we reported to category management and buyers that purchase various things, and they wanted ad hoc reports to see how certain programs were doing, how certain products were doing, how certain product lines were doing. And because the items were changing, they had their regular weekly reports, but there was also a lot of ad hoc analysis being done. And we use structured query language. And these are just commands to send instructions to a database to perform tasks like creating items and querying existing data. And these commands are classified into languages based on their purpose. This table shows all the various types of querying language. We have DDL, which stands for Data Definition Language. And this changes the structure of a database by adding or subtracting tables and relationships. Most accountants don't do this. This is usually left to database designers and computer designers. Then we have the data manipulation language that modifies the data within a database. Once again, not something that you typically will do as an accountant. Then we have data control language, which grants access to or removes access from a database user. Once again, IT function, we as accountants should not be controlling access. Then there's transaction control language, which interacts with the DML, so the data manipulation commands, when transactions are processed in the database. Same thing, not something accountants are going to be doing. What we will be doing is using data query language, and this retrieves data from a database on user's request. And the main command is select, and this begins all retrieval process and reports when you are using a database. Let's look at an actual select command. So remember that SQL statements are just syntax used to communicate SQL commands to the database. And a simple SQL statement starts with the term select, which is entered in the query window. And this command retrieves data from the database. And in its basic form, what you're writing is select. And then you're identifying the field name that you would like to select and from which table that field is in. So for example, if we're looking at the customer order table and we would like to select customer names, so we would say select customer name from customer table. And then to retrieve all the columns in a specific table, you just use the little star sign. And multiple columns can be selected by adding a column between the names of the different columns. So select field name, as many fields as you would like, from, and then the table name. So for example, if I want to know the customer name, but I also want to know the customer ID, and I also want to know the customer's payment information. From the customer table, I can query all those columns. And you can add a where clause to filter which records the query returns by adding values such as mathematical comparison. So let's say I have a customer named Jim Mills and I would like to only retrieve Jim's data. I would write select customer name from the customer table where the customer equals Jim Mills. If you have dates, you can use greater than or equal to, less than and equal to, or does not equal. So for example, if I want to look at all our customers but Jim Mills, I would say select customer name from the customer table where the customer does not equal Jim Mills, and we can also use between, like, or in our query statements. We can also join different tables together to get information, because as we talked about earlier, relational databases are about relationships and they don't store all information in one table. They're stored in multiple tables, so our join operator retrieves interconnected data from related tables by declaring the primary key and foreign key relationships as the join column. And join operators are classified by the desired results of SQL statements. A join can be either inner, so within the circles, or outer joins are further classified into 3 types, depending on which set of records are desired. All 3 outer joins return values that are not present in both tables. So we can have an inner join, which is just overlapping between the 2 tables. We can have a left outer join where we are getting all the information from our table A, but only the information that interacts table B. This example is the opposite. We're getting all the information table B, but only the portion of table A that interacts with table B. And then a full outer join is you're getting all the information from all the tables. Thank you for watching this lecture. I hope you found it helpful, and I'm looking forward to seeing you in class. Have a great week, everyone.